So far, we have learned 4 values related to stress and strain, 2 types of stress, nominal stress and true stress, and 2 types of strain, nominal strain and true strain. Previously, we mainly used only nominal strain and nominal stress in calculations, and then we got new values, the true strain and the true stress. You should now clearly understand the equation that describes the relationship among these values. Here, I am demonstrating the true strain can be derived from the nominal strain. The ratio of the original length L0 to the final length L can be deployed as shown here. So, the equation for true strain is expanded as the equation. This equation includes the definition of nominal strain, epsilon equal to L minus L0 divided by L0, that we have used so far. So, the true strain can be transformed into the equation. You should be noted that the true strain is determined by using nominal strain. This formula enables us to determine the true strain with the results of tensile test. Then, the equation that defines true strain includes log. Thus, the relationship is obtained by using exponential. We now recall that the true stress could be written as sigma L divided by L0, which has been derived under the assumption that the volume is constant. Substituting it into the above equation yields the equation. This equation implies that the true stress can be defined in terms of nominal stress and true strain. The equation that defines true strain is given as the form that includes log. We further transform the equation by using exponential. L divided by L0 is exponential to the power of true strain, 1 plus epsilon. Substituting it, we finally get the equation. The equation gives the true stress in terms of nominal stress and nominal strain. Using these equations, you can convert nominal and true strain and nominal and true stresses each other. For example, if you have a calculation software like Excel, the easiest way to find the true stress and true strain is to use the equations for nominal stress and nominal strain. Here, you should understand the relationship between nominal and true strain and true stress and true strain with respect to the equations. When should we use true strain and true stress? When the strain is very small, the difference between nominal and true strain is very small. So, for problems that deal with small strains, nominal strain and nominal stress is sufficient as previous cases. Here, note that the problems of small strain are equivalent to elastic problems. In the elastic region, since the strain is very small, so using nominal strain and nominal stress causes no problems. When dealing with problems of elasticity, we do not usually use the terms of nominal stress and nominal strain. We simply call them as strain and stress. In the later discussion, you may not see true strain and true stress so often. So, I would like you to sometimes remind that the strain and stress used in problems of elasticity are nominal stress and nominal strain. When the strain is large, from a few to tens %, the cross-section area changes significantly from its initial value. It becomes thinner like noodles. In such situation, the nominal stress does not define accurate quantity. So, we need to use the true stress followed by the usage of true strain. Typical example may be approximation model of a nonlinear stress-strain relationship. By determining the relationship between true stress and true strain, various material parameters, such as work hardening coefficients, can be determined. These parameters can be determined from the results of tensile tests. In this meaning, the true stress and the true strain is more important when the deformation is large. These concepts are included in solid mechanics, so you may remind the argument introduced above when learning the new concepts of solid mechanics. You may firstly try to understand the meaning of nominal stress rather than nominal strain. The nominal stress is an approximate stress, assuming that there is no change in cross-section area. So, you may be a bit feel uncomfortable to use the nominal stress for calculation. However, in the differential equations in material dynamics, if you do not use nominal stress and nominal strain, the calculations include nonlinearity. Let me explain about the problem of nonlinearity in detail. Nonlinearity makes differential equations more difficult to be solved. So, when the strain is small, keep the linearity is a better way to solve the differential equations. So, we try to use nominal strain and nominal stress as far as the situation allows. When dealing with large strains, we perform calculations by using true strain and true stress. So, you may understand that nominal strain and nominal stress are used to solve problems in the subject of material dynamics. This approximation becomes nonlinear in plastic field. With more complex approximation of a phenomenon, differential equations inevitably become nonlinear. This is not only true in material dynamics, but also in fluid dynamics and thermodynamics. In other subjects, the equations may change depending on such approximation methods. In such cases, you may remember that a similar case was in material dynamics.